Good morning, everybody. So I'm Michael Flessner, Extension Weed Specialist at Virginia Tech. I have the pleasure of introducing Cynthia today. So she's originally from Texas, did her undergraduate at Cornell. She got to work with, here in weed science, the great Antonio D. Tommaso while she was there. And a familiar face to PSA, Eugene Law, she got to work with him as well there. She went on to Texas A&M for a master's in weed science under another familiar face to the digital weed space, Muthu Bhagavathian, and then she came to Virginia Tech in 2020, which is a fun year to start a new transition. But she's done really well here. Her dissertation research that she's going to talk about today really focuses broadly on weed management with cover crops and how we can optimize management there. So management of the cover crops. I don't want to take any more details away from her, but within the PSA group, she has led 5 or 6 on-farm installations in Virginia the last couple of years, and we've got another year of that coming up this season. And she also led a CE2 installation in 2021 that we did. So she's been working tremendously hard and is really passionate about this area of research. And so I'll turn it over to her.
All right, thank you, Michael. I'm gonna try and share my screen here, and hopefully everyone can see that. All right. So yeah, thank you, Michael, for the introduction, and thank you all for your time this morning. I'm really thankful to get a chance to share some of the research that we've been working on. And today we're going to be looking at 2 objectives that I've been working towards my dissertation that are going to help us look into the question of, can we reduce herbicide or fertilizer inputs when using cover crops? And so let's see here, there we go. And so we, as weed scientists, a lot of our focus and goals are to stop herbicide resistance or to control this from being a much bigger issue than it is. It's a quite big issue in our agronomic production systems. And as weed scientists, it's our goal to not only suppress weed populations, but to stop herbicide resistance from continuing to develop, or to at least slow it down. And one of the tools that shows a lot of promise in the area of weed suppression is the integration of cover crops into our production systems to help manage these weed populations. And we know from previous research that cover crops are really a really strong tool to use to suppress even some of the most troublesome species, such as Palmer amaranth. I really enjoy showing this picture. It was taken by Dr. Lynn Sosnowski and Dr. Stanley Culpepper, and I just think it shows the potential of a cover crop to suppress, like I mentioned, even some of the toughest weeds like Palmer amaranth. This was in cotton, and you can see the cereal rye that had been rolled under, but you can see the difference in weeds and weed populations here. And so I just think that's such a great example of the potential that cover crops hold for weed management. And so even though we know the benefits and what cover crops can do for our farmers, there are still a lot of questions that, that we don't really have clear answers to. A lot of the questions that we get from farmers revolve around the area of termination timing of a cover crop. And this is valid because this time is really critical in cover crop management. The timing of termination, ultimately, that's when you have the total biomass accumulation by that cover crop. And we know from previous research that biomass accumulation is really one of the strongest, if not the strongest, driver of the weed control that we see in the early spring. And so it's a really critical time. And that's why we get so many questions revolving around it. And there's also other questions about nutrient management, which I'll get into in the second part of this presentation. But for now, we're going to focus on the weed control. And so when a farmer plants a cover crop, the goal is to have something like what we see on the left here. It's heavy biomass and high coverage of that bare ground. And so what we don't want to see is what we see on the right is uncovered ground that allows for weeds to poke through that are then going to have to be controlled later on. So really the goal is to have something like on the left where you're covering that ground and protecting and outcompeting weeds that are trying to poke through. But when it comes time to terminate that cover crop, a lot of our farmers use what we call a brown termination. And this is typically a termination timing that occurs about 2 weeks prior to the time of planting. And so by the time the farmer comes in to plant, the cover crop is brown, it's dead, like what you see in this picture here. But we also have farmers who are experimenting with what we call a green termination timing. And so you can see the difference here. The farmer is planting into a green and living cover crop that is was still very much growing at the time of planting. This is actually from one of our farmers in the northern neck of Virginia who has been working with us. He's actually part of the PSA program. We were on his farm this past year, and he's been looking at this and experimenting with it. And so in order to provide better recommendations for our farmers, we developed 2 objectives with this project. Our first objective was to determine the effect of a cover crop termination timing and see how that affects Palmer amaranth emergence patterns and growth rates. We chose Palmer amaranth because it is one of the most talked about weed species in weed science, and it's a troublesome weed that has developed resistance to multiple modes of action. And our second objective was to use the results from the first objective and optimize our herbicide programs. So to try and figure out if we can make our herbicide programs better, and ultimately to transfer that to our farmers. So from previous research, we hypothesized that yes, we think the cover crop termination timing is going to impact emergence patterns and growth rate of Palmer amaranth. And because of that, we're going to be able to make changes to our herbicide programs and provide better or different recommendations. So in order to carry out these objectives, we developed an experiment. This started in the fall of 2020. All of our field locations were located at the Kenland Research Station close to Blacksburg, Virginia. So in the fall of 2020, we planted a cereal rye cover crop at 75 pounds to the acre, and we allowed that cover crop to overwinter. And then in the early spring, we started our terminations. So we had a planting date set to the first week of May for both years. And we were planting E3 soybeans into that cover crop. So 2 weeks prior to that cover crop plant, or to that soybean planting, we terminated our brown treatments. And then 2 weeks later, at the time of planting, we terminated the green treatments, or the treatments that were going to be green. And we also had a no cover check for comparison. And so those were our 3 main treatments. But in order to answer the question of Palmer amaranth emergence and growth rate changes, we also developed or made subplots within these main plots. So I'll show you here. The initial termination of the cover crop was done by applying Liberty at 32 ounces to the acre to terminate that cover crop at the designated times. You'll notice here that the green termination is 2 weeks later than the brown and no cover. And so this was our planting dates. And every 2 weeks, we'd come in with an application of Liberty, and we would spray a little bit less of every plot. And by doing that, we established these subplots that essentially became Palmer amaranth cohorts that we could then follow throughout the duration of the experiment. And that way we were able to track the growth rate of these Palmer amaranth plants as well as emergence patterns. And so this is what the plots looked like. This is an example of a plot that had a cover crop. I don't quite know if this was a green or brown termination, but this is one of the cover crop treatments, and then you have the no cover on the right-hand side. And so you can see the subplots that were established with these yellow stakes. And if you look towards the back, these were the subplots that received earlier applications, but were also we didn't apply as many applications of Liberty. And so you can see the difference in the Palmer amaranth density there. And so our data consisted of taking records of how long it took for these subplots to, we mostly focused on how long it took the subplots to either reach 10 plants per meter squared, so the density of the Palmer amaranth, or we also looked at the amount of time that it took a single plant in a subplot to reach 4 inches in height. And we used those two metrics because we thought that those were two thresholds that a farmer would say, okay, I have 10 plants per meter squared, it's time to spray. Or the plant is reaching 4 inches in height, it's time to spray. And so those were the thresholds that we established. And so we calculated the number of days to reach those two thresholds. And today I'm going to be showing some simple descriptive statistics just to show the data that we have accumulated over the 2 years. And so we're going to get into the results of this first portion. So in 2020, we're going to do 2021 followed by 2022. And the first set of data that I'm going to show is the number of days that it took from that initial burn down application to the time that it required a post application. So that was either when we had 10 plants per meter squared or when a single plant reached 4 inches in height. And so that's the number of days is on the y-axis. And then we have our time period on the x-axis. And so 2021 was quite an odd year. It was very dry in May and June. And I mention that because I think that's important. And I think that drove a lot of the results that we saw in 2021. But as you can see, this data here shows us that the brown treatment, it took longer for those Palmer amaranth plants in the brown treatments to reach a point where a post application was needed compared to the no cover and the green treatments. I'd like to show you 2022 now, and this is the same collection, the same data collection, the days from the time of that initial burn down to the time of a required post. And this, I think, more closely resembles what we expected to see, where you see a longer number, or like the longer time period in the green and the brown treatments to reach the point where we needed a post application compared to those no cover treatments. Along with this data, I also thought it was important to show the density of these plants. And so here we're showing the Palmer amaranth density at the time of the required post application. And then on the x-axis, we still have our same time periods. And again, 2021 was a little odd, I think, because of that moisture that just was not available. And it really took longer for the plants to start getting their startup. But we see that at 6 weeks after burn down, we see the no cover just completely taking off in terms of density of Palmer amaranth plants in those subplots. In 2022, the same pattern, I think more normal, more closely to what we expected to see, but the no cover plots were just consumed with Palmer amaranth plants. And we really see a reduction in density, in weed density in our two cover crop treatments. And so that's kind of what we saw. 2021 was just really strange, I think, because of that drought. But I think 2022 shows more closely what we expected to see. Now, in order to complete the second objective, we decided to integrate some economics into our project. And so we ran a simple economic analysis. And in order to do this, we associated several costs to different programs. So for example, we associated a $38 per acre cost to putting a cover crop in the ground. We associated a $25 cost for a residual herbicide, a $14 cost for a single post-application herbicide, and so on and so forth. And what we did is we we looked at every treatment and we matched every potential combination. So we had a brown termination with a single post application, a green termination with 2 post applications, no cover with a post and a residual. And so we made all of those possible combinations, and we looked at which one of those programs is going to keep us weed free until those soybeans have the opportunity to canopy. And so that's what our goal was, to reach less than 10 plants per meter squared, or to avoid plants getting to a 4-inch height up to the time that those soybean plants could canopy and then be home free at that point. And so in order to run this analysis, we had to use a few assumptions. We assumed a 28-day weed control period for a residual herbicide. We also associated a $9 per acre cost to an application. So every time a tractor would go over the field, we associated $9 as a cost for that. We also made the assumption that our post herbicide applications would control all weeds present, but as many of you may know, that doesn't always happen, and it's just an assumption we had to make this analysis. And again, the programs that we selected and compared, we were pretty restrictive. First, by setting those thresholds of 10 weeds per meter squared, or 4 inches in height for a single weed, and then making sure that those programs would take us to a soybean canopy. So after looking at all of those programs, we found that in 2021, surprisingly, the most successful programs that would take us to the time of canopy, as well as the most economic programs, were a single post application herbicide. And that was true for every treatment that we looked at. And similarly, in 2022, the most successful and economic programs were 2 post applications in that case. And I chose to show the most economic and successful programs for every treatment, but I will mention that when we looked at it overall, the first and second place, if you will, for most successful and economic programs were actually the no cover treatments. And I think a lot of that had to do with the cost association that we considered here. I think it's important to mention that, you know, we tried to match the cost as closely as possible to current numbers, but those costs are always changing. And in the case of cover crop, you know, a lot of times there are subsidies that need to be included. And if a farmer is growing their own seed, that's a cost that's going to be zero, essentially. And so these numbers are really fluid, if you will. So some of the take-home messages that we wanted to share from this project were just that we did in fact see changes of germination and growth patterns for those Palmer amaranth plants, and termination timing, I think, was able to influence, especially just compared to our no cover plots. And because of this, I think there is potential for us to optimize our herbicide programs, even though that economic analysis wasn't, I don't know, it wasn't what I expected to see, but I think, you know, it's a case-by-case scenario, I think, by farm. And I think there is potential there for our farmers. And just a few things that I wanted to mention. Again, 2021 was just so dry in May and June. And I think that really influenced the germination patterns that we saw. I remember just going out into the field and there was just no Palmer amaranth there. And I was like, where is it? And so I think that really, the drought really delayed a lot of the germination. And in some of those cover crop plots, the cover crop was holding enough moisture that we saw earlier emergence in some cases. So I think that year of drought really skewed some of the data that we were seeing. And then finally, again, the economic analysis that we did was very limited, and there's a lot that can be changed. And I'm sure multiple ways that it can be improved, but we just wanted to kind of get started and put a dollar value to what these programs would look like for a farmer. And additionally, there are a lot of savings, of course, that can be associated with the use of cover crops. And so we're going to start going into the nutrient benefits that we can see from a cover crop for our second portion of the presentation. And so we're going to shift gears a little bit and talk more about fertility. We're not going to leave the weed science behind, but along these lines of benefits that can be provided by the cover crop, we talked about the weed suppression capabilities, but there's also a lot of research out there that shows that something like a hairy vetch can provide up to 100 pounds of nitrogen per acre, which is something definitely not to look over and can be incredibly beneficial for our farmers. And again, although we know of these benefits, these agronomic systems are complex. You know, we have a lot of questions from farmers that want to get started into cover crops, but there's a lot that isn't understood and isn't fully communicated. And a lot of what we think about is how, you know, if a farmer goes through the effort of putting a cover crop into the ground, a hairy vetch, for example, where they're trying to reap some of those nitrogen benefits, a lot of the worry is that some of that nitrogen is not going to reach the cash crop, that it may either be lost or taken up by weeds. And a lot of this is still unclear as far as the dynamics of having a cover crop presence, but then having weed competition and nitrogen not being taken up by something like corn. And so we wanted to explore this a little further, and we developed two objectives for this trial. So our first objective was to determine if the presence of a cover crop can suppress weeds enough to reduce competition for nitrogen. And we were really focusing at the earlier stage during peak nitrogen demands, and that's what we chose to focus on. And our second objective was to determine if the presence of cover crops, along with strong herbicide programs, could potentially reduce the amount of supplemental nitrogen that would have to be added to a corn crop. So so we believe, based on previous research, we think that cover crops will be able to suppress weeds enough to reduce that competition for the nitrogen. And you know, based on strong herbicide programs combined with cover crops, that we could potentially reduce the nitrogen required. So in order to carry out these objectives, we established studies at two locations in Virginia. The first one was in Blackstone, Virginia, and the second was in Suffolk at the research stations there. So we had two locations across 2 years for a total of 4 site years. And so in the fall of 2020, we planted a cereal rye and hairy vetch mix, and we allowed that to overwinter. And right before, or at the time of corn planting, the first week of May, we rolled that cover crop, and then we planted corn through it and applied 30 pounds of starter nitrogen for that corn to get started. So we focused on 3 main factors. The first factor was either the presence or the absence of cover crop. And so you can see here, our first treatment was just a no cover. You can see that in the picture. And then our second treatment was just cereal rye, which was at 75 pounds to the acre, and hairy vetch at 20 pounds to the acre. And so those were our 2 treatments for our first cover crop factor. The second factor we looked at was the herbicide, and this was composed of 2 treatments. The first was what we called a Weedy treatment, and so those plots received glyphosate and atrazine at 32 ounces to the acre at the time of planting, and that was the only herbicide application that they received. Our second treatment was what we called the weed-free treatment, and that received glyphosate plus Lexar-EZ, which is composed of these the last 3 active ingredients mentioned there, and that was at the time of planting. But then additionally, we came back at the time of V4 when the corn reached the V4 period, and applied Halex GT at 3.6 pints to the acre. And so that got a stronger herbicide program. And finally, our third factor was our fertility program. And so this was composed of 6 different nitrogen levels. They were all applied at the time of V4, and they ranged from 0 pounds of nitrogen to the acre all the way to 200 pounds of nitrogen to the acre. And so this is what our plots look like. Our weedy plots were in fact quite weedy, and our weed-free plots were pretty clean. We had a few escapes, but definitely our treatment establishment was pretty successful in that case. And so ultimately, these efforts culminated at the time of harvest when we collected yield data for every plot. And then we used that data and ran it in SAS, and we used generalized linear models to make contrast statements for factors of interest, which I'll be showing here in a second. And in order to complete our second objective, we determined agronomic optimum nitrogen rates in order to figure out, can we reduce the amount of nitrogen needed for the corn crop to increase yield there. So I'll get into the results here. We're gonna start off with our contrast statements. And so this first contrast statement table is focusing on the nitrogen competition coming from the weeds. And so our first column here is our treatment number. The first number is always the weedy plot, and the second number is always the weed-free plot. And then columns 3 and 4 describe the cover crop and the nitrogen treatments. And finally, our last 2 columns are the p-values associated with these contrast statements for each location. So starting off, this first contrast statement is a weedy plot with cover crop and no nitrogen at side dress compared to a weed-free plot with cover crop and no nitrogen at side dress. And so we see here, we didn't see any significant differences. And the same is true for the second and third contrast statements. And so really what this is telling us is that where nitrogen was limiting either with or without the cover crop, the herbicide programs were really not enough to make a difference in corn yields here. But then as we move forward and we look at our third and fourth contrast statements, we see here, we don't see significance here, but under the presence of nitrogen and when we had a cover crop, the herbicide program didn't make a difference. But when we applied a side dress application of nitrogen and the cover crop was not present, that herbicide program was able to increase corn yield at one of our locations. And so that's our first set of contrast statements. The second set of contrast statements is looking at the nitrogen contribution coming from the cover crop. And the layout is the same as the first one, except that our first treatment number here is reflecting the no cover plots, and our second number is reflecting the cover crop plots. But the same layout is true for the rest of the table. And so we start off seeing no significant differences for a situation where you don't have side dress nitrogen, a strong herbicide program, and we see that the cover crop here was not able to make a difference. But as we move further down our contrast statements, we start seeing more interesting results and significant values. So here, where nitrogen was limiting, and you have a weedy competition present because of a weaker herbicide program, we see the cover crop kick in and was able to increase corn yield here at the Blackstone location. And when we move further down our contrast statements, it gets a little more interesting. We see that when nitrogen was present and we had those side dress applications, either in the weed-free program or in the weedy program, we see that cover crop kicking in and being able to increase the corn yields observed. And so we can speculate as to why that is. This last contrast statement, we had weed competition. And so we can say, maybe the cover crop kicked in the sense that it provided some weed suppression. And then we looked at our third contrast statement here, and we see, the weed program was strong. So maybe this could be more due to moisture retention by that cover crop. As I mentioned earlier, 2021 was so dry. And so maybe some of that moisture that was being provided by the cover crop helped increase corn yields in this situation. But we see a clear difference where nitrogen is present compared to when it was not sufficient. Next, we're going to move on to looking at our agronomic optimum nitrogen rates. And so we're going to look at this by our two locations. On the x-axis, we have the nitrogen rates at side dress, and on the y-axis, we have our corn yields. And these formulas show, the blue shows the weedy treatments under the cover crop, and the orange shows the weed-free treatments under cover crop. And so what we did is we used these models to find the optimum nitrogen rate. So at the point where this line starts shifting, right? And so what we did is we found the derivative of this formula to solve for X. And so X would be the optimum nitrogen rate. We then plugged in that optimum nitrogen rate into our formula to solve for Y, which would give us the predicted yield at that optimum nitrogen rate. And so this is what we found. We saw that the weed-free program did have a higher expected yield, as we would expect, than the weedy program. And when we looked at the optimum nitrogen rates, we didn't necessarily see a decrease. We still had a higher optimum nitrogen rate for the weed-free program. But that's just what we saw in our results. And when we look at the second location, we used the same methodology to come up with our numbers. And we saw pretty similar trends where the weed-free program had a higher expected yield. But then when we look at the optimum nitrogen rate, it is a little lower in this situation. And I think there's a lot that can be discussed there and that we can talk about. But those are some of the preliminary results that we're seeing right now. And so here, some of the take-home messages that we wanted to share. In terms of our first objective, we really saw that the main driving force was really the nitrogen that was either present or absent when we look at those contrast statements. That was a huge driving force in ultimately the corn yield that we were observing. And regardless, the cover crop alone and the weed program alone were really not sufficient to drive corn yield and to have a significant difference there. We did see that the cover crop improved corn yields at many sites. And like I mentioned earlier, we can think about why this is. And in some cases, we can speculate that some weed suppression was being provided, or maybe a little bit of nitrogen was being provided. But I think because of the type of year that we had, especially in 2021, a lot of that could be attributed to moisture retention provided by that cover crop. And so, yeah, it's important to take into consideration the kind of year that we had, and these nitrogen optimums were different in terms of when looking at our two locations. A lot of data, we have a lot of data that we want to include here concerning like soil sampling that had taken place at the beginning of the year that I wish I could have included in this presentation. But I just didn't think I had the time to do so. So that's another thing to consider. And finally, our Weedy herbicide program had an application of glyphosate and atrazine. And atrazine is a really strong herbicide, especially in corn. And that could have potentially taken us through the critical weed-free period in our corn crop. So that's another thing to just consider when looking at the results of this study. We do have a lot of data that we want to include, like I mentioned. We had soil testing done on these plots. We also have grain nitrogen and ear leaf nitrogen samples that I think could complete this story a little better. But for the sake of time, that was not presented today. But there's a lot that goes into this, and it was a really great opportunity to be part of this project, because as a weed scientist, a lot of times I just focus on the weeds, and the agronomics are not always in my head, I guess. But it was really great to be able to incorporate different forms of thinking with this project. So that's all I had to share today. I want to thank the extension program and Dr. Flesner for all his help. Wade Thomason, who is now at Oklahoma State, was also a huge part for that second objective that we looked at. And Dr. Josh Mott has helped tremendously with a lot of the data analytics. So I want to mention them and thank them for all of their help. And if there are any questions, I'd be happy to answer them. And hopefully it was worth your time to stop by and listen today.